Welcome to the physics class for February the 4th. This is for the A-Day class. Now, I am also going to use this recording for the B-Day class. I'm going to post it on Canvas. So hopefully you guys understand that next week, Monday, Tuesday, Wednesday, all of us teachers are going to be off at a conference that Principal Wilson has signed us up for. And so what I'm going to do for the B-Day class is I'm going to post this video on Canvas, and I'm going to send them all a note telling them all to watch this video and treat it as if it was a live video. Hang on just a sec, somebody just got here. Let me mark them tardy and let them in. Okay, so if you're in the B-Day class, treat this as if this was a live video. And do the homework and everything just as if this was live. All right, so before we get into the physics stuff, all right, so first thing is the schedule for next week, which I've already talked about. So for those of you in the A-Day class, and also I'm not quite sure how I'm going to handle it for the B-Day class, but for sure the A-Day class, what I want you guys to do is log in to Canvas on Monday. And don't be surprised when I'm not here live, but what I will do is I will have a video posted where I'm going to have you guys do a lab, except the equipment that you need to do the lab, you don't have. So instead, what I'm going to do is tomorrow, so on Friday, I'm going to go into the school because I go in every Friday because of robotics and things. So I'm going to Shanghai a couple of robotics students, and I'm going to have them do the lab in place of you, and while I video it. And so you're going to watch what they do, and you're going to make careful notes, and then I'm going to have you write up a lab report as if you had done the lab yourself. So you'll write up a lab report describing it, and I'll put a rubric on Canvas like we normally do. So I think that's the plan for that. Now, as far as Wednesday of next week goes, for those of you in the A-Day class, I haven't quite figured out what I'll do there. Probably, well, we'll see. But I'll post it on Canvas. All right. Okay. Another announcement. All of the Chapter 14 quizzes, I have now unlocked them so that you may now go back and retake them as many times as you need until you get a 10. So please do that. Now, as I've said many times, when I transfer it from Canvas into Aspire, I'm going to transfer it in manually, not automatically. And so first thing is you need to tell me that you've retaken it. If you don't send me an email telling me that you've retaken the quiz, I'm not going to know. Okay. And then the second thing is when I transfer it from Canvas into Aspire, even though you've got it, even though Canvas is going to say you got a 10, I'm going to transfer it in as a 9. If you want to get a 10 on it, you got to get a 10 before the deadline, not after. Now, if you were to get an 8 on it and you decide that you're not going to bother retaking it to get a 10, you're just going to live with the 8, then what I'll do is when I transfer it into Aspire, I'll leave it as an 8. You know, what I really probably should do is subtract 1, but I'm such a nice guy. Sometimes it scares me. So yeah, so I won't do it. And then the last announcement is just remember tutoring, guys. Every Tuesday, every Thursday after school, and then also on Fridays and Saturdays at different times. So please take advantage of tutoring. So if there are no other questions, then I will go ahead and talk about last night's homework. Any questions? Okay, so Aurora is asking, so on Thursday, am I going to have a Zoom meeting? Okay, so the plan is that on Thursday, we will be back. We teachers who are off to this conference, we will be back live again on Thursday as if it was a regular day. So for those of you in the A-Day, well, it's not going to help you because we don't meet on next Thursday. But those of you that are on the B-Day, yeah, Thursday of next week will be a regular day, and I will be here live. Oh, really? What I'm responding to is Aurora typed a note into the chat box, a private note, so the rest of you can't see it, saying that next week the A-Days and the B-Days are switched. That's news to me. I will have to look that up. I don't want to take time right now. That's news to me. Okay, then and Taiwan just yeah, Austin just confirmed that. Okay, that is definitely news to me. I don't see any note about that. Tell you what, I will send a note off to Principal Wilson and say, hey, what's this weird rumor? And I will send you guys all an email. Once I know what's happening. Okay, so let's talk about last night's homework. Here are the answers to the ones that you haven't already looked up in the back of the book. As usual, if you could only see one problem worked through, please tell me in the chat box what you would want that one problem to be. Now, actually, I'm thinking we can probably do more than one today because I don't have as much new material to give you as I would on a typical day. So hopefully we'll have time for two, but if you could only see one, what would it be? So I'm seeing a vote for 78 and 20, 77 and 78 and 80, got a bunch of them. So 77 is getting a bunch of votes. Oh, okay, 77 is clearly winning here. But also 20 is getting a couple of votes as well. Okay, so tell you what, let's do 20 and also 77. I'm pretty sure we're going to have enough time to do both. And then if you guys want to see some of the others work through, then stick around at the end of the class. We'll work through them at the end of the class. But 20, I agree, is a good one. 20, and in fact, 20 is especially good because, you know, this lab that I told you that I think I'm going to have you guys do a lab report on next week is basically problem number 20. Yeah, that's what the lab is going to be. All right. So let me open up a whiteboard. All right, so in problem number 20, they say that we've got a tuning fork and we don't know the frequency of it, but we're going to hold it above an error column like the kind that you see in example problem 2. So if you didn't do problem number 2, if you didn't read the book before you did the homework, and if you didn't spend a little time looking at example problem number 2, which is on the same page here as problem number 20, then you probably didn't understand what in the world they were talking about. But I trust that you read the book before you did the homework, right? I know you always do that. And so let me draw a picture of what's happening in example problem number 2 at the top of the page on page 416. Because this is what I'm going to have some students do on Friday. They're going to do this very same thing, and I'm going to take a video of them doing it with a little bit of a twist, but only a little twist. Okay, so basically what we're going to have is we're going to have a big column, a big cylinder, and the one that I have is at school is clear, so you can see through it. So it's really helpful. And then we're going to have a bunch of water in the cylinder. And then we're going to have a smaller tube, smaller diameter. And we're going to start off with the tube mostly submerged, but not completely. And this tube is going to be open on both ends. So it's open on the bottom and it's open on the top. Now the outer tube is of course closed on the bottom because if it wasn't, all the water would leak out, but it's going to be open at the top. All right, and then what we're going to do is we're going to take the tuning fork and we're going to whop it on our knee, and then we're going to hold it up above this column here, this tube, which is submerged in the water. All right, and then what's going to happen is that, so the tuning fork is sitting there vibrating, and it's designed so it vibrates at one specific frequency. And actually, I have a whole collection of these tuning forks. And so I have one for each different frequency that I might want over a fairly large range. Okay, so as this thing is vibrating, it's going to send sound waves down the column, and they're going to hit the water, and they're going to reflect off of the water. So this is going to, so Sam thinks I'm a nerd. You're right, nerd, and I'm proud of it, Sam. Okay, so it's going to hit the water and it's going to bounce back up. It's going to behave like a closed pipe oscillator. So last time we talked about the different types of musical instruments, and we talked about wind instruments, and we talked about the fact that there are two different kinds of wind instruments. And in fact, I even have a copy of the slide that we used last time. Okay, so what you're seeing here, this is what we called a closed pipe wind instrument. It's actually open at one end, but the other end is closed, so we call that a closed pipe wind instrument. And then the other possibility is to have an open pipe wind instrument. That's where it's open at both ends. Notice the difference. When you have an open pipe wind instrument and you have a sound wave that's resonating inside it, you will always have a node at each end because it's open to the atmosphere. And so the pressure can't be anything other than atmospheric pressure at the end. But inside the tube where it's enclosed, you can have a little bit higher pressure. But if you have a closed pipe, okay, so which is what we have here, because when the wave hits the water, the sound wave cannot escape. So it behaves like a closed pipe. So notice what we have here, and let me turn on annotation so I can draw. Okay, so at the top here where it's open to the atmosphere, the pressure wave is a node because it can never be higher than room pressure or lower than room pressure. But down here at the bottom, when the wave hits and it's bouncing back, as the wave hits, then there will be a high pressure region there. And then when it bounces back, there will be a low pressure region there. So we're going to have an antinode there. And so if the wave that's resonating inside the pipe there is what we call the fundamental frequency, so that's the lowest possible frequency, it's going to look like that. But if it's a higher frequency, it can look like this. And if it's a still higher frequency, it can look like this. But notice we still have a node at each open end, and we still have an antinode at the closed ends because that's what it has to be. All right, so that's what's happening here. Let me go back to my whiteboard. All right, so what we're going to do when I film this tomorrow with a couple of volunteers, and by the way, if any of you are in the robotics club and can come tomorrow to help out, that would be good because we'll do both robotics and we'll also do physics as well. Okay, so what's going to happen here is when we get if we shorten the pipe down to the lowest place, well, actually, also another thing I should tell you is that we're only going to get resonance if everything matches. And when I say everything, what I mean is the length of the pipe has to be just right, the frequency has to be just right, the speed of the wave through the air has to be just right. If everything is just right, what we'll get resonance. And if everything's not right, we will not get resonance. So what does that mean? Okay, well, it basically means the same thing as what we had with our Coke bottle and the water in the Coke bottle. Remember, I blow across here. So what I did for you guys was I blew across here and we got resonance. And even when I changed the water level, we got resonance, but it was a different frequency of resonance. Okay, so when I blow across the Coke bottle, I'm actually blowing a whole bunch of frequencies. All of the frequencies are contained in the that I do. But if I take a tuning fork, and so let's pretend this is a tuning fork. I'm holding that tuning fork above it. I don't have a collection of all different frequencies. I have only got one frequency. Okay, and so when it sends the sound wave down there and it bounces back up, if I just pick any old tuning fork at random and pick any old length here at random, the odds of it resonating are very, very slim. And so what's going to happen is when I hold this tuning fork above here, I'll hear the tuning fork with its really faint sound, but I won't hear anything resonating down here in the bottle. But if I adjust the water level here and I keep on adjusting it and until the magic happens, what's going to happen is when it gets to the right height where everything matches, the frequency and the length and the velocity, when it all matches, that faint sound is going to become a very loud sound. It won't be faint anymore because it'll be resonating. And you'll see this when I do the video tomorrow. Okay, so let's go back to the whiteboard here. Okay, so when we start off in the video that we're going to do tomorrow, we'll start off at just any old random height here, and you won't hear anything special. And then what I'll have them do is I'll have them take this inner pipe here, and I'll just have them move it up and down. And when we get to the magic height, that faint sound will become a very loud and then we know that we've got resonance. Okay, so when we're at resonance, okay, if we are at the lowest possible height that resonates, the wave that we're going to see inside the pipe there, if you could see a sound wave, you know, which we can't, but if you could see a sound wave, well, what we would see is that there would be a node at the top and there'd be an antinode at the bottom. That is what the wave would look like that's resonating in there. Okay, and then what I'm going to do is I'm going to tell the students, I'm going to say, okay, now raise the pipe up higher, and that resonance tone will go away, and we won't hear it anymore. So let me switch to a different color pen here, and a different size pen. Okay, so what we're going to do then is, so the outer pipe still is the same as it was before. The water level is still the same as it was before. But what we've done now is we've raised that inner pipe there, the inner tube there. And that's not a very good drawing. Let me see if I can fix that. Okay. So now this inner pipe there has been raised to a higher thing. So when we raise it up above this level here, that resonant loud that we hear is going to go away. But if we keep on raising it up and up and up, we will reach another magic point, a point where if we have this tuning wave up here, we will reach a point where we'll hear that really loud again, because it'll resonate a second time. And if we were to draw what the wave looks like inside there, well, the rules are you have to have an antinode at the top, and you have, or I'm sorry, node. Sorry, you have to have a node at the top, and you have to have an antinode at the bottom. But this time, we're going to have a node right here, and not coincidentally, that node is going to be at the same height where it was before. And then there's going to be an antinode in the middle, and then here, an antinode. And so this is what the wave is going to look like if you could see a sound wave when the tube gets pulled up higher. Okay, so we'll get resonance here, and then as it goes up, we'll lose the resonance. And then when the pipe gets up to here again, we will get resonance again. And so this is what they're talking about in example problem number 2. And so what they're saying in example problem number 2 is, let's go up there. They're saying that they hear a resonance the first time when the top of the pipe is 21 centimeters above the water. And then as it goes higher than that, then they lose resonance. But then they get resonance back again when the pipe is 65.3 centimeters above the water. That's when they get resonance again. Okay. And so, so Aurora is saying that she just did this for an 8th grade science fair project. She just didn't do the math. Well, good. So now you're going to do the math. Now you're going to finally understand what it was you did back in 8th grade. All right. So what that means is the distance between these two nodes here is going to be whatever is 65.3 minus 21.0. That will be the distance between the nodes. All right. So in example problem number 2, which I recommend you get out your book and follow along here. So when they do that, okay. So well, actually, let me just do it here. So 65.3 minus 21. I don't need a calculator for that. Why did I get out a calculator? All right. So 44.3 centimeters. That is the spacing between the nodes. Okay. Now, is that the wavelength? So I want to pause for a second here, and I want all of you guys to type in the chat box in a private message. Don't make it be a public message. Make it be a private message. I want you to answer yes if you think that is equal to the wavelength, and I want you to type no if you think it's not the wavelength. Okay. All right, and I see one of you just said, if any other teacher had asked this question, I would have said yes. But if Mr. Hendricks is the one that's asking it, then I'm suspicious. So good for you. Yes, you should be suspicious. No one, no one trusts me, Sam says, and good. And well, you should not. Okay, so the first person to say no here was Will. So Will, why did you say no? Can you unmute yourself and tell us what's the reason why you said that this is not equal to the wavelength? If you're talking, Will, I'm not hearing you. Can you unmute yourself?
Is this working now? Okay,
Yeah, I can
cool.
hear you now. Why is that not equal to the wavelength?
So basically two of those little rotations make up a wavelength, right? Based on what you said last time.
Okay,
So
good.
yeah.
All right, all right. I like what he said. He said it differently than I did, but you know, that's a good way to say it. So if I were to draw a wave, just okay, so there we go. There's a nice wave, a whole bunch of cycles, right? And I want to ask, okay, how much of that is one wave length? All right, well, if we start at the node and we go up to the antinode, actually, let me make that be a fatter pen so it shows up a little better. If we start at the node and we go up to the antinode and come back to the node, that is not a wave. Okay, in order to be a wave, we have to go all the way down and back up. Now that, okay, there, that is a wave. All right, so we started here at the node, so that's there. And then here's the first, oh, I'm sorry, I'm looking at the wrong one. Well, okay, yeah, that's good. Okay, so then here's the antinode. Okay, so that's there. And now here is the next node, so that's there. So if we stop right there, we have not gone one full wave. We've only gone half of a wave. So what that means is 44.3 centimeters is not the wavelength, but we can look at that and we can know what the wavelength is, because we know that 44.3 centimeters is actually the wavelength divided by 2. So if we multiply both sides by 2, then what we find is that the wavelength is actually 2 times 44.3. And so that's what they did in example problem number 2. All right, so, and then once we know the wavelength, we can use everybody's new favorite equation, lambda equals V over F. So if we know what F is, and we didn't know what lambda was before, but we do now, so now we can find out what is the speed of sound. And that is exactly what we are going to do in the lab that I'm going to have a couple of students do for me tomorrow while I'm at school. And then I'm going to have you guys write a lab report about it. So make sure you understand what we just did. Okay, now with all of that big, long introduction out of the way, now let's look at problem number 20. And so what they're doing is they're saying that the resonances are not spaced by 44. They're saying that the resonances are only spaced by 20.2. Okay, so what I need to do then, let me open up a new whiteboard. All right. So what they're saying is that somebody else does the experiment um, with a different tuning fork now, but it's going to work the same way. Okay, so here's the outer tube, here's the water level. So the first time they do it, they get a wave that looks like this. And then the second time they do it, here's the water level, so the tube is up higher now, all right? And so what they find is, so if you look at the wave inside the tube, it's going to look like this, okay? And so in problem number 20, we're saying that the node spacing here is not what it was in example number 2. It's different because we're using a different tuning fork. And they're saying that the spacing here is 20.2 centimeters. All right. And so we want to know what is the frequency of the tuning fork. So we got lambda equals V over F. So this time the frequency is what we don't know. But lambda we can figure out quite easily. If we look at this, and remember this is not lambda, this is lambda over 2. So that means that lambda must be twice what that one was. Okay, so our new lambda for problem number 20 is going to be 40.4. But remember, that's centimeters. And we want to work in standard physics units. So let's write that as 0.404 meters. That's the lambda that we want to use. Okay, so now we know what lambda is, so we can plug it in for here. We don't know what the frequency is, so we need to find for that. Now, what about V? V is the speed of the sound wave as it rushes down and rushes back up. Now, up until now, we've always said that V was 343, but that is only true if you're at room temperature, which is 20 degrees centigrade, and also if you are at sea level. Because if we're up here in Utah, the air is a little bit thinner up here. And so it should not be a surprise that the speed of sound is a little different up here in Utah. So tomorrow, when I go into the school and I have a couple of students do this, what we're going to do is we're going to measure the speed of sound. And don't be surprised if you find that the speed of sound is not 343, even if the temperature is 20 degrees C, because the air is a little bit thinner up here. All right, so you're going to be tempted to use 343, except if you look at when you looked through example problem number 2, you found out that the speed of sound that they got was not 343. The speed of sound they got was 347, and that was because the room temperature was not 20 degrees C. The room temperature was higher. And so in problem number 20, what they're saying is assume that it's that same higher room temperature. So they're saying for V, don't use 343, use the same V that we got in example problem number 2. All right, so from this point on, it's no longer a physics problem, now it's just a math problem and you're good at math, right? All right, so what we want to know is we want to know the frequency. So let's take those guys and let's swap places. So we get F equals V over lambda. So V for problem number 24, problem number 20 is 347. Okay, and lambda is going to be not 20.2, it's twice that. So it's 0.404. Okay, so when we do that, we find out that the frequency of this mystery tuning fork that we're using is, so I get 858.91 blah, 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 blah. And it looks like they want 3 sig figs, so I'm going to have to round that up. So 859 hertz. That is the frequency of the mystery tuning fork. And let's just go back here and make sure that that agrees with what they had before. If not, I'll be very embarrassed. 859, okay, yay. All right. So problem number 20 was oops, wrong one. There we go. All right, problem number 20 is a great problem. I want everybody to spend time on it and make sure you understand it. Not only does it teach you important physics that I guarantee I will put on a test, on the test, but also it helps set you up so that you'll be in a good position to do the physics lab report, which I'm going to give you as a homework assignment next week, because we're basically going to do what you've just seen. We're going to do it for real. And what we're going to do is we're going to measure what the speed of sound is here in Utah, which will be different from what it is at sea level. Okay, I realized that took a while. And so you might be worried that we don't have a lot of time left, but I think we'll be good because I don't have a super amount of new material to give you today. So we can go back and do the other one. Was it 77? Yeah, it was 77 was the one that won the most votes there. Okay, so let's do 77. What do we got here? Okay, so we got a string instrument. Let's open up a whiteboard. Actually, tell you what, before we open up the whiteboard, let me go back to here. And let's make sure that you guys are really comfortable with string instruments and how they work. Okay, so these 3 slides, this is a string instrument. This is a wind instrument, which is open on both ends. So we call it an open pipe wind instrument. So that'd be like a flute, okay? And this is a wind instrument that's closed on one end. So we call it a closed pipe. And so that would be like an organ pipe. Okay, so notice the pattern. If you just focus your attention on the fundamental frequency only, so that would be, so this is the fundamental frequency. So notice we have a node at one end, we have an antinode at the other end if it's a closed pipe wind instrument, okay? But what if it's an open pipe wind instrument? Well, then it's going to look like this. So if it's an open pipe wind instrument, then we have a node at one end and a node at the other end, okay? And notice that the harmonics follow the same pattern. There's always a node at the end, and there has to be, because if it's open to the atmosphere, the pressure at that point can only be atmospheric pressure. Inside the tube, it can be higher or lower, but outside, it has to be equal to atmospheric pressure. And so it has to be a node at either end. Okay, now what about a string instrument? Well, a string instrument, like, a violin or a guitar, the string is fixed at either end. And so by definition, it has to have a node at either end. And so the mathematics for a string instrument are exactly the same as the mathematics were for a open pipe wind instrument, okay? These equations that you see right here for the fundamental frequency, and right here for the first harmonic, and right here for the second harmonic, they are the same equations. Now, V is going to be different because if it's a wind instrument, V is going to be 343 if you're at room temperature and at sea level, okay? But if it's a string instrument, V is going to be different because for a string, the medium is the string, not the air, okay? So the number for V is going to be different, but the equations that govern what's going on, they are the same. This is the equation for the fundamental. This is the equation for the first harmonic. This is the equation for the second harmonic. They're the same. All right, so what we've got here in problem number 77 is a string instrument like this. And the string is 65 centimeters long. So I'll tell you what, let's just do it right here. So this L here is 65 centimeters. So that's 0.65 meters, because I prefer to work in standard physics units. And so when we pluck the string here and we get out some sort of a sound measuring tool, it tells us that the frequency that we get, the fundamental lowest frequency, is 196 hertz. All right. So we want to know what is the wave in the string. So you remember, whenever you have a standing wave here, what's happening is you have wave pulses that are traveling left to right, and they hit the end and they bounce back, and they interfere with the ones that are traveling right to left. And that's what creates this standing wave. And so if it was a wind instrument, then V would be the speed of sound in air. But this is not a wind instrument, it's a string instrument. And so V is going to be different. So we're going to have to use everybody's new favorite equation. Lambda equals V over F. And so if we know that L is 0.65, and we know that we got a node here and a node here, we know that that is equal to lambda over 2, not lambda, but lambda over 2 for the same reasons that we just talked about before. So if we double that, then that tells us then that lambda is going to be 1.30. So now we know what lambda is, and we know what the frequency is, so bingo, we can solve for V. So if we multiply both sides by frequency, that goes away. So V equals F lambda. So F is 196, lambda is 1.3. So when we do that, we find out that the speed, so 196 times 1.3. So the speed of this wave is 254.8, which is too many sig figs. So let's see, I think they want to, yeah, they want us to use 3 sig figs here. So we're going to call it 255 is the answer. And this is V. So as long as we put the numbers in standard physics units, they're going to come out in standard physics units. So that's going to be meters per second. And so there's the answer for part A. Now, part B is saying what are the next 2 higher frequencies, the next 2 higher resonant frequencies? Well, we can just use these equations for that. If it is a string instrument, or if it's an open pipe wind instrument, the first harmonic is going to be whatever the fundamental was times 2. And the second harmonic is going to be whatever the fundamental was times 3. So all we have to do is just take 2 times 255 and then come back again and take 3 times 255 and bingo, we're good. Okay, so that's how it works. And that same pattern works if it's an open pipe wind instrument. Okay, notice that if it's an open pipe wind instrument, then the first harmonic is twice whatever the fundamental was, and the next harmonic up is 3 times whatever the fundamental was, but only if it's an open pipe wind instrument. If it's a closed pipe wind instrument, the pattern is different there. If it's a closed pipe, the first harmonic is not 2 times the fundamental, it's 3 times it. And then the next harmonic up after that is not 3 times the fundamental, it's 5 times it. And the next one after that is 7, and then 9, and then 11, and blah, blah, blah. Okay. So I'm hoping that this helped. I'm hoping that now all of that stuff that didn't quite make sense before, now hopefully it's making sense for you. Yeah. In fact, tell you what, can you give me some feedback? Give me a yes or no if you think you understand things a lot better now. Type in yes to the chat box and make it be a private message. So, and if it's a no, then be honest. Okay, so I'm seeing a lot of yeses. Okay, I am seeing a no. So thank you for being honest. So that one person who said no there, and that second person who said sort of, then maybe after we finish class today, if you stick around and we talk a little bit more, maybe we can help get it fully for you there. But for right now, let's move on to the new. And by the way, no, the person who just said I'm just stupid, you know, of course, that's not the case. This is a little bit tricky. And by the way, I know that you were kidding. All right, so let's talk about the new material now. Yes, okay, yes, I'm glad to see that you agree that you were just kidding. All right, so today we're going to finish up chapter 15. The stuff that we're going to do today is not going to be as calculator intensive. I mean, there is going to be some math, but not like we did before. Mostly it's just understanding why things do the way that they are. So we have a word for that. We say that it's going to be more qualitative than it is quantitative, right? But there is going to be some math involved. All right. So let me start off by asking, first of all, if I were to do an experiment where I asked you to close your eyes, and then I were to get 2 musicians to come into the room, and they have 2 different instruments. Let's say one is a flute and the other one is a violin, although it doesn't really matter, just 2 different instruments. And what I'm going to do is I'm going to tell them to play the exact same note. So middle C, or whatever. Pick some musical note. Let's make it be middle C. Okay, now you are the in the audience, so you're sitting there and you've got your eyes closed. And so what I'm going to do is I'm going to silently point to one of the musicians, and they're going to play their instrument. And then and then they're going to stop, and then I'm going to point to the other one, and they're going to play their instrument. Now they're both playing the exact same note. So you sit there with your eyes closed. Would you be able to tell the difference? Could you tell the difference between a flute and a violin if they're both playing the same note? I'd like you to type into the chat box. Say yes if you think you could tell the difference. Say no if you think not. Remember, they're playing the exact same note. Okay, it looks like it's overwhelmingly yes. Okay. Let's see, Gia, you were the first person to say yes. Can you explain to me how is it possible? In fact, tell you what, I'm going to play devil's advocate here. I'm going to open up a whiteboard. Okay, and I'm going to draw a picture of what middle C looks like. Okay, so here is a wave, and I'm going to pretend that the frequency that I used is exactly the right frequency, so that it's middle C. And then I'm going to change the color of my pen here, and I'm going to draw a picture of the other musical instrument playing the same wave, right? So that means the frequency is the same. My frequency there wasn't the same. Let me see if I can make it be a little better there. So let's see if I can make the frequency be the same. Okay. All right, so there's two sound waves, both of which are middle C. Now, Gia claims that she could tell the difference. Okay, so Gia, how would you be able to?
Just because the instruments sound different, because one's just made by blowing air into it, and then the other one's just made by rubbing a string against a metal string, so they just have a different noise.
Okay, I agree with everything that you just said, except that I don't agree that really explains it, because if they're both playing the same note, they both have the same frequency, why is it different? Now, actually, Connor and Aurora are onto something here. Aurora, in fact, she used a special word, and she did it in a private message, so the rest of you weren't able to see it. So the word that Aurora used is timbre. Except if you are a music student, your music teacher might pronounce that differently. They might call it timbre. It's spelled timbre, and most physicists pronounce it as timbre. But I've found that most musicians, for whatever strange reason, they look at this word and they pronounce it as timbre rather than timbre. So Aurora, you're the one that used the word here. Can you unmute yourself and tell me what is this timbre of which you speak?
It's kind of like it adds character to the sound, so it like it's depends. It's basically describing the quality of a sound or a voice because of its pitch and intensity.
Not so much the pitch and intensity. I agree with everything else you said, but I disagree with the pitch and intensity. So let me explain it this way. When I drew these waves and I said that the upper one was the wave from a flute and the lower one's a wave from a violin, I lied. If you were to actually take a photograph of the sound waves, what you'll find is that the two waves do not look the same, even though they do have the same frequency. So what you're going to find is this. Okay. So the wave on the left is the wave that you'll get from a tuning fork. That's what the book likes to call pure sound. The wave on the right, that's what you get from a clarinet. Now, these are both the same musical note. So remember, the musical note, or the pitch, that is determined by what is the frequency of the sound. So if we look at this graph here, we notice that the independent variable in both cases is time. So if I were to ask you, what is this to this? The answer is not the wavelength. If our independent variable here is time here, this distance right here represents the period. And so if you look at the period of this wave that comes from a tuning fork, and you compare that with the period of this wave that's coming from a clarinet, okay, you'll see that the period is the same in both cases. And since the period, so the period, which is capital T, right? That's 1 over F. So if the period is the same, that means the frequency is the same. So the tuning fork here and the clarinet here, they are both playing the same note, but the shape of the wave is different. It is, for the clarinet, it's not a sine wave. It has the same period as the sine wave does, but it's not a sine wave. All right, so why is that? Well, okay, so now we get into some really interesting musical theory here. So what I'm going to do here is I'm going to draw a picture of a guitar, or it could be a violin or whatever. But okay, so here is this figure 8 thing, and it's it's got a hole in it right there, and then it's got this like a neck on it, and the strings are all going across here like this. So this is the guitar. So this figure 8 thing that I drew is called a sound box. That sound box is very, very important. If that sound box wasn't there, you'd have trouble hearing the note, and the note that you hear would not sound like a guitar. So think of it this way. Let's say that here's my guitar string. All right. So I pluck the string. Now I heard that just now. In fact, let me do it again. Let me put it in my teeth here. Okay. I'm going to pluck this string. Tell me if you can hear it. I heard it. Did you? Probably not. Okay. So when you're playing your guitar, if all you had was the string without the sound box, you might be able to faintly hear it, but your audience would not. Okay, so the sound box is really important. What happens is when the wave is sitting here vibrating, so let's pretend that this piece of paper here, this is the sound box. So the string is connected to the sound box. So when the string vibrates, it causes the sound box to vibrate. Every time the sound box moves towards you, it pushes a bunch of air. And then when it moves back, then you have a low pressure, and then it moves forward again, which is what the string was doing too. But the string is so small, it can't push very much air. So your audience is not going to be able to hear it. But if you connect it to a sound box, it causes the sound box to vibrate. And so now, because the sound box has more surface area, it pushes more air. And so now your audience can hear you. But it does more than just increase the volume. It changes the timbre. It changes the sound quality. It changes the flavor of the sound. So here's what's happening here. Okay. So when you get a wave, let's say you've got a fundamental frequency here. So here is the fundamental frequency. This is maybe what the string is doing. But the string is setting up vibrations in the sound box. And depending on what materials the sound box is made of and how thick they are, the vibration that they pick up will be related to the string frequency, but not exactly the same. So like, for instance, it might be twice what the string frequency is, or it might be 3 times. So here, what I need to do here, oops, sorry, that's not what I wanted. What I need to do here is to call on Desmos. Oh yeah, Calvin just sent me a private message. Yes, Calvin, you're onto something. You're definitely onto something. But let me explain it this way. Okay, so I'm going to use Desmos. Let me open up my I don't know how my browser got closed there. Let me go in real quick. Oops, oh, that's how my browser, it's okay, try it again. Hang on just a second here. Okay. All right, so now let me share my screen with you. Okay, and so let's go into Desmos and open up the graphing calculator. All right, so what I'm going to do is I'm going to show a mathematical representation of a wave, just a generic wave. So the simplest wave that I can think of is y equals sine of x. Okay, there you go. So let's suppose that this is the wave of the string on the guitar. Now, whoops, okay. So when we play that string, it is going to excite some vibrations in the sound box that will be related to the string frequency, but not exactly. So like, for instance, it might be the first harmonic, or it might be the second harmonic, or some of you call it overtones, right? Okay, so let's say that these excited wave is, it's got twice the frequency. So if we were to put that in Desmos, okay, so it's looking like that, okay? And it might even excite the next harmonic up above that. So let's say y equals the sine of 3x, okay? All right, so what's happening is you don't just have the fundamental frequency, you have all of these frequencies together, all resonating at the same time. Now, what's that going to look like? Because your ear isn't going to hear them separately, your ear is going to hear them all together. So this is what your ear is going to pick up. You're going to pick up this. So you get the first fundamental wave, but at the same time, you're getting the first harmonic, okay, and at the same time, you're also getting the next harmonic up above that, okay. So this is what your ear is going to hear. So let me turn these guys off temporarily, okay. Look at that wave. That is not a sine wave. That is a very complex, very interesting wave. The timbre of that wave is very different. Let's see how it's related to the fundamental. Okay, look at the relationship here between the periods of these two waves. Okay, so if we start off right here, okay, so the blue wave does a whole bunch of funny dances, and then when it starts off again, so from here to here, that is one wavelength for the blue wave. But if you look at the green wave, or what is that, red, whatever, if you look at the other wave, you'll see it starts off here. So they both have the same period, okay? So that means they are both playing the same musical note, but your ear can definitely tell the difference there, okay? The sound flavor, or the official word is timbre. The timbre of these two musical notes is going to be very different, even though they're both playing the same wave. Okay, so the sine wave, that would be a very simple instrument, like a tuning fork, and the more complicated wave, that would be a much more interesting sound. That would be like the violin. Now, what's the difference between a Stradivarius violin and a Walmart violin? They're both violins, right? But someone who's a professional musician, they can tell the difference. So tell you what, let's get a new equation in here. And let's start off by just copying and pasting the original equation. Okay, so I've got two equations and they're both the same. So the blue one, that's one violin, and the black one is another violin. And right now they're both exactly the same. But let's suppose that one of them is a Stradivarius and the other one is a Walmart violin. So the difference is the Walmart violin is made of cheaper materials. And so the thickness are a little different and the materials are different. Now the frequencies are going to be the same, but the amplitudes are going to be different because it's made out of a different kind of wood. So let's change the amplitude of the fundamental. Let's say instead of having an amplitude of 1, let's have it be an amplitude of 0.8. Okay, and let's say that for whatever reason, the first harmonic, instead of being a little bit less, maybe the first harmonic is a little bit more. So let's say it's 1.5. Okay, and then the third harmonic, let's say that, you know, for whatever reason, maybe it's a little bit less, so it's 0.75. Now we can see a difference. Okay, now you can see that they're similar. So to the untrained ear, you would hear that and you'd say, yeah, they're both violins, but a professional musician would be able to tell the difference. Okay, they would say, oh, that one is a Stradivarius, and the other one, that one's not a Stradivarius. I don't know where it comes from, but it's not a Stradivarius. Okay, because even though the frequencies are the same frequencies, the amplitudes, you know, when we mix in the harmonics, we mix them in with slightly different amplitudes because they're made of slightly different materials and different thicknesses, right? So that is timbre. Or if you're a musician, they usually prefer to call it timbre. Okay, timbre, timbre, same thing. All right, so in your homework tonight, they'll ask you some questions about that. There's not a whole lot of mathematics that you're going to have to do, as mainly as just being able to explain in words what we just talked about. Okay, now there is one other thing that you're going to need to also know for tonight's homework. And the best way to explain that is by hearing it. Okay, so let's go back into my Chrome browser. Let's go to Canvas. Let's go into the physics page. Now you guys know I've put a whole bunch of really neat software simulations into Canvas here. I really strongly encourage you to play with all of these different fun things that I put on here. So the online pendulum simulator, the online mass on a spring simulator, you know, watch the Tacoma Narrows Bridge, the online wave reflection simulator, all these neat things, play with them. But there's a new one now, the online sound frequency musical tone beat frequency generator. Okay, so if you click on that, it takes you to here. Now, first thing is you'll notice I've told you what the frequencies are of the various musical notes. And okay, so that's one thing I want you to know. And in the chat box here, a couple of you put in some comments that I didn't really say anything about, but you talked about octaves. Well, this is what an octave is. Okay, so if you look at all these notes right here, they are all in one octave. And if you so we have C, what's called middle C, and then we have another note which is also called C, and another note which is also called C. They're just in different octaves. And if you look at the relationship, you'll notice that when you go up one octave, the frequency is twice the previous octave. And you go up another octave, and again, it's twice the octave. So every time you go up one octave, what you're doing is you're increasing the frequency. And it doesn't matter if you're talking about C, or maybe you're talking about F sharp, okay? If you go from F sharp in one octave to F sharp in the next octave, all you've done is you've doubled the frequency. That's what octaves are all about, which is cool, but that's not really the thing that I came here to show you about. The thing I came here to show you was actually this other thing up here. So there is a link right here. I want you to play with this on your own, but let's play with it right now. Wave interference and beat frequency. This is really cool and really important. Okay, so what I can do is I can have two musical notes here with two different frequencies. So let me start off by having them be the exact same frequency. So would you guys like to hear what 250 hertz frequency sounds like? Well, here it is. Let me get rid of this thing. He's in the way. Okay, that is what 250 hertz sounds like. Okay, now what if I increase the frequency? Let's take it up to 400 hertz. And I'm going to take both of them. Well, I'll make them be different in a minute, but for right now. Okay, all right, so let's hear what 400 hertz sounds like. Okay, that's 400 hertz. Okay, now here's the fun part. What if I make one of the notes be slightly different? So instead of it being this lower one being 400, I'm going to make him be 401. Okay. let's see what happens when we turn on the sound. Hear that? You hear that throb, that kind of wah, wah, wah. Okay. What you're hearing is called a beat frequency. The two waves that are almost the same frequency, they're interfering with each other to where they'll interfere constructively for a fraction of a second, and then they interfere destructively for another fraction, and then they interfere destructively for another fraction of a second. Okay. Now, what happens if instead of them being only different by 1 hertz, what if I make it so that they're different by 2 hertz? So let's play that. Notice the wah, wah, wah is happening at a higher frequency than it was before. The first time we did it, you were hearing about 1 wah per second. Now we're hearing 2 wahs per second. Let's take it up here one more. Let's take it to 403. Okay, so let's listen to what the beat frequency is now. So we're hearing 3 wahs per second. Okay, so this is going to come in very handy for your homework tonight. Okay, they're going to ask you what they call the beat frequency. Okay, and they're going to say, okay, we've got a frequency that's some number, we've got some other frequency that's some other number. They're going to ask you what is the beat frequency, and it turns out to be incredibly simple. Whatever is the difference in the frequency between these two guys, that is the frequency of the wah, wah, wah that you're going to hear. Okay, so so this turns out to be really, really easy. Now, what if that second frequency, instead of being higher, what if it was lower? So instead of 400, what if it was 399? Okay, so the difference in the frequency this time is a -1 rather than a +1. Let's see what that does here. It's the same. Okay, so it turns out it doesn't matter whether you take F2 minus F1 or F1 minus F2, it's the absolute value of the difference between the frequencies that determines what your beat frequency is going to be. And you're going to find that to come in really handy in your homework tonight. Now, let's see if we can understand why this is the case. So let me go back to this. Okay, so I'm going to have a difference of 5 hertz. And so I'm going to hear 5 wahs per second. It's kind of hard to tell because it's so fast, but that's 5 wahs per second. Let's see if we can figure out what's going on and why. So this is the first wave, this is the second wave. Let me click on the box here that says overlay. Now what you're going to notice here is that when the two waves are laid on top of each other, right here in the middle, they are lined up perfectly. So when the two waves hit, we're going to get what's called constructive interference, which is a word that you've heard before. But as time goes on, they get a little bit out of phase, out of sync. And when you look over here, you can see that they're not quite lined up anymore. So we're not getting the full constructive interference. And in fact, if we zoom out on the time scale here, so let me do this. You see what happens? Okay. And in fact, tell you what, let me make it a little bit more pronounced here. Let's go like this. Okay, now you can see it even more. Okay, so right here in the middle, let's say this corresponds to t equals 0. And so the two are lined up perfectly. So what we get is constructive interference. And when we come over here to this little bit right here, so it's 0.045 seconds later here, then we now have they've shifted to where they are out of phase. So they are, in this case, they are completely out of phase. And so they are interfering destructively. So you get a quiet thing. And then it comes back being in phase again. And then it just repeats. And so that is the beat frequency. And so in the book, they talk about it, and I think they do a pretty good job of describing it, but nothing is as good as actually hearing it for yourself. So hopefully you guys have now heard it and now you understand it. So in your homework tonight, when they talk about beat frequency, that's what they're talking about. Okay. Well, that's pretty much it, I think, for chapter 15. Can you guys think of any questions that you want to ask? If not, then I'm willing to let you type bye into the chat box and head out. Oh, you probably want to know what the homework is, right? Okay, I can see how that might be helpful. Now, obviously, you can just look on Canvas because it's on Canvas, but here you go. All right, so here's the homework. Make sure that you don't forget to take the daily quiz. And any of the older quizzes, if you need to retake those, go ahead and retake those. And if you want to discuss any of the homework problems or anything at all, but you don't want you to be recorded doing so, let me go ahead and turn off the recording so we can talk without embarrassment.